Welcome back, engineers. This video we are looking at another wheel and axle complete problem. This one is about a doorknob being turned. Let's read. Extremely excited to get to engineering class, a student applies a force to the edge of the doorknob of 0.6 pounds. The locking mechanism pushes back with 1.4 pounds. The student spends 0.7 foot-pounds of energy while turning the knob. Calculate the ideal mechanical advantage of the doorknob system. How much of the energy spent was converted to useful energy by opening the door? Okay, before we get started, let's identify some givens and let's understand what we're looking at here. Let's look at the diagram first. The doorknob is the larger piece being rotated. That's our wheel. And the axle is kind of the peg that goes inside the door and engages with the locking mechanism. So we do have some information. We do have the radius of that wheel, which is 0.9 inches. And this is going to be our effort distance. Notice that this D does not stand for diameter. This stands for just distance that the effort force is from the center of rotation. Okay, so that's our DE. Now we do have a measurement over here. This is the diameter of the axle, which we will have to cut in half to get the resistance distance. So let's cut that in half right now. It's going to be the resistance distance is half of 3. We could just write 3 over 2, which is going to give us, of course, 1.5 inches. Okay, so let's put those things on our givens list. DE is 0.9 inches and DR is 1.5 inches. Or sorry, not 1.5, it is 0.15. That's what happens when you don't use a calculator, folks. Let me correct that really quickly. Erase this. This is 0.15 inches. Okay, so let's carry on here. What other givens do we have from the problem? We have 0.6 pounds up here was our effort force. That's how hard the student is pushing to rotate the doorknob. And the resistance force, 1.4 pounds. And we also had an amount of energy given to us. The student spends 0.7 foot-pounds of energy. That's going to be our energy input. And that's going to be 0.7 foot-pounds. Okay, first thing we can do is find the IMA of this system. I'm going to do that now. Because we have the effort distance and the resistance distance, we can just do this in one shot. DE over DR. That's going to give us 0.9 over, that's a 9 there, 0.9 over 0.15. These are both in inches, which will get canceled out. Let's pull up our calculator. 0.9 over 0.15, we get 6. So our IMA of 6. Remember, the wheel is where our effort force is being placed on that big doorknob, right? So there's a lot of leverage that the effort force has. So our IMA should be greater than 1, which it is. Let's find the AMA next. FR over FE. So that's going to be 1.4 pounds over 0.6 pounds. Let's do that in our calculator. 1.4 over 0.6 2.33. There must be a lot of friction in this system because our AMA is much, much lower than our IMA, but that's okay. That can happen with lots of machines. So we've got our AMA, we've got our IMA. Next thing we should probably do is find percent efficiency. So remember, the equation here is percent efficiency equals 100 times AMA over IMA. So that's 2.33 over 6. Let's go to our calculator. 100 times 2.33 over 6, 38.8% efficiency. Like I said, our AMA was far off from our IMA, much lower. So we should expect a low percent efficiency. We got 38 point, what was it? 38.8. 3 sig figs is always enough for us, and will be accurate to carry our calculations through to the end. So I always round off to 3 sig figs. 38.8. Do we have any of the answers yet? Let's see. Ideal mechanical advantage was calculated already. We found that to be 6, and there would be no unit for that because the inches would have canceled out. And we're asked how much energy spent was converted to useful energy. So this will be our last calculation for the problem. I'm going to kind of do this at the bottom here. So at the last step here, we're going to find the useful energy. Useful energy is found by taking our percent efficiency divided by 100 and multiply that by your energy input. So I'm going to fill those values in over here. Percent efficiency was 38.8%. Divide that by 100 and multiply by the energy that was input, 0.7 foot-pounds. So this is where, again, you could just type in your calculator here. You could just do this yourself and just switch over that decimal point 2 spots to be 0.388 and multiply that by 0.7. I'll type in the whole thing here just for good measure. 38.8% divided by 100. That's going to give us, if I hit equals now, 0.388. Multiply that by 0.7, which was our energy amount, and that gives us 0.272 foot-pounds. So out of that 0.7 foot-pounds that the student spent, a small fraction of that, 38% of it, is actually used to open the door, and that's 0.272. Alright, hopefully this helped. Good luck with the rest of the problem set.